Good morning. I am Daniela Renga from the Politecnico di Torino. I'm going to present a work carried out in collaboration with the Federal University of Minas Gerais. This work is about the use of small solar panels and small batteries to reduce the carbon footprint in radio access networks. The energy consumption of base stations in radio access networks largely contributes to the operational expenditure faced by mobile network operators. Indeed, the base station energy demand accounts for 80% of the total mobile network consumption. In addition, it is expected that by 2022, the global mobile data traffic will have increased by almost sevenfold with respect to 2017. And this means that mobile networks will be more and more densified, leading to a further worsening of this problem. In this context, solar energy represents a viable solution to power base stations where the electric grid is not reliable or where it is not available at all, for example, in some remote region, but also to decrease the mobile network operator operational costs. However, the deployment of a solar panel system requires typically huge surfaces, so large that the solar panel deployment may become problematic in some urban environments where there are a lot of physical constraints. With our work, we aim at investigating if the use of small area solar panels and batteries with a limited capacity in combination with a smart energy management allow to increase the amount of green energy that is used to run the base station and to reduce the operational expenditures for mobile network operators. To do this, we use Markov reward model approach to evaluate the performance and the overall energy cost of the base stations that is equipped with a renewable energy generation system and that is controlled by an energy management unit. We implement also different energy management policies to compare the different performances. Having a closer look to our system, we have a single macro base station belonging to a mobile network operator that can be powered by the renewable energy produced by a photovoltaic panel set or by the energy that is harvested in the storage or by the electric grid. The storage can be used not only to harvest any extra amount of energy that is renewable energy that is not immediately used, but also to store some extra amount of energy from the electric grid that can be stored in the battery for future usage and that is drained from the power grid when the electric costs are lower. All these energy exchanges are managed by an energy management unit. We built a discrete time Markov reward chain model for each of the 4 seasons. Each state Z in this model is defined by 3 state variables. First, the date type W that depends on the renewable energy production. And there can be 5 different day types. Second, we have the time of the day, T, with a now 1 hour granularity. And finally, we have the irradiance level, L, which depends on the day type and on the time of the day. The graph reports the irradiation levels for different day types that we have in the summer season and in the winter season, just as an example. The battery charge level is a continuous random variable that is represented by the accumulated reward gained at each time that the discrete time Markov reward chain visits state Z. Here we have the formula for this battery charge level, for this reward. Ez is the amount of the energy that is produced by the photovoltaic panels in state Z. And this depends on the panel capacity and on the irradiance level. Then we have Cz that is subtracted since it is the amount of energy that is consumed by the base station in state Z. It depends on the time of the day and on the traffic profile that we are considering. Finally, AZ is added as the amount of energy that is acquired from the power grid in state Z, and this depends on the energy purchasing policy that we are implementing. Regarding the model parameterization, the energy production depends on the irradiance level that in turn is a function of the day type and the time of the day. To compute the transition probabilities between different day types for each season, we consider real data from a long-term data set of 20 years about the daily solar irradiance. In addition, to model the intraday variability, we use the real data from a data set of just 2 years, containing real data about the hourly average irradiance. And finally, as actual value of solar irradiance, we use the real value from the city of Turin, Italy. The energy consumption of the base station depends on the data traffic profile. We consider two areas for the traffic profile, a residential area in blue and a business area in red. The dashed lines represent the weekend and the solid line represent the weekday. We see that in the business area, we have some traffic peaks during the central hours of the day, during the weekday, while in the weekend, the traffic is almost negligible for the entire day. In the residential area, the traffic gradually increases in the morning hours to achieve a peak in the late afternoon if we are in the weekday, or to achieve a peak in the late evening if we are in the weekend. Furthermore, the energy consumption depends also on the power consumption model. We are considering the FP7 Project Earth model, whose reference is reported at the bottom of the slide. As we were mentioning, we tested 3 different policies that we have implemented. The only battery policy envisions that brown energy is acquired from the grid only when the solar energy from the photovoltaic panel or the energy stored in the battery is not available to run the base station, so when the battery is empty also. The night consumption policy basically operates like the only battery policy except during the nighttime from midnight to 6 a.m. In this period, brown energy is acquired from the grid in a quantity equal to what is necessary to run the base station, so no energy is drained from the battery at all. Finally, the night consumption and recharge policy operates like the night consumption policy, but during the night, we draw an additional amount of energy from the grid and store it in the battery for future usage, and this amount is equal to half a kilowatt hour or 1 kilowatt hour per hour. So we have 2 different versions of this third policy. Coming to the numerical results, we report results considering a scenario of 1 base station in a residential area, considering a weekday. Also, we assume that there might be some charge and discharge losses in the charge and discharge process of the battery of 15%. And finally, we consider small values for the capacity of the panel and the battery. In particular, for the panel sizes, we have 1 to 5 kilowatt peak corresponding to area occupancy between 5 and 25 square meters. For the battery, we consider 1 to 5 kilowatt hour corresponding to 1 or 2 car batteries. Here we report for the case of a 1 kilowatt hour battery, and under the application of the only battery policy, the energy demand from the grid over a year on the left y-axis represented by the red bar, and on the right y-axis the cost. The cost includes the capital expenditures for the photovoltaic panel, in orange bar, the capital expenditure for the battery in the yellow bar, and these capital expenditures are average yearly capex, meaning that they are derived by averaging the total capital expenditures over the expected lifetime of the photovoltaic panel or the battery, respectively. Then we have the energy cost in the blue bar and the total cost, including the capital expenditures and the operational expenditures for the energy in the light blue bar. The dashed line in light blue represents the cost in the baseline scenario, assuming that no renewable energy generation system is present, and so all the energy must be bought from the grid. We report a similar result considering increasing values of the battery capacity and also for all the other strategies. We can observe that under all strategies, considering the highest size of photovoltaic panels, 5 kilowatt peak, the cost for the total cost when a renewable energy system is present becomes higher with respect to the energy cost in the baseline scenario. This becomes even more evident with the larger batteries, considering even smaller photovoltaic panel size, like 1 kilowatt peak, in which the total cost is higher than the baseline scenario, in which no renewable energy system is present. And this trend holds for all the strategies. Considering the night consumption and recharge policy in the two versions, we can say that considering any photovoltaic panel size, the total cost result at least equal or higher than the baseline cost. So it is not convenient to use these policies in terms of cost. Regarding the only battery and night consumption policies, when we have a small photovoltaic panel size and small batteries, we can have a small cost saving. Even if this cost saving is small with respect to the baseline scenario, we can have a relevant gain in terms of green to brown ratio. By green to brown ratio, we mean the ratio between the amount of solar energy that is used to power the base station and the amount of energy that is drawn from the grid to power the base station. And clearly, the highest values can be achieved under the only battery and the night consumption policy. And in particular, even with intermediate values of photovoltaic panel size, like 2 kilowatt peak, we can have a green to brown ratio higher than 1, meaning that more than 50% of 50% reduction of the carbon footprint can be achieved. Concluding, in our work, we modeled a base station system powered by a renewable energy generation system using Markov reward models. We investigated 3 different energy management policies. The first one, envisioning that brown energy is drained from the grid only when the battery is empty. The second policy envisions that during the night, base station is powered through brown energy only. And finally, the third strategy envisions that during the night, some brown energy is proactively stored in the battery for future usage. Our results show that a small overall cost saving can be achieved, and huge carbon footprint reduction can be obtained by more than 50%, even using rather small photovoltaic panel sizes, requiring an area occupancy of less than 10 square meters, and using the equivalent of 1 or 2 car batteries as energy storage. So our results demonstrate that the adoption of a hybrid power system for base stations become feasible in a large number of scenarios, including urban environments where there are a lot of physical constraints. This concludes my presentation. Thank you for your attention.